Hi, everyone. Thank you for joining us today. This is our interview with Dr. Nana Ofori-Opoku. My name is Jeremy, and I'm joined with Kevin, and we are part of the Computational Materials Society at McMaster, where our goal is to try to inform students on the connection between material science and programming concepts. Nana, if you wouldn't mind, would you be able to give us a little bit background about your current role and maybe where you've worked in the past, just as a general background?
Yeah, sure. So right now I am an assistant professor in the Material Science and Engineering department. What I assume everyone will probably find out, but I did do all my degrees at McMaster, surprisingly. So undergrad, master's, and PhD. I did my PhD, graduated in 2013. I did spend the last couple of years of my PhD at McGill University. At that point, my advisor, Nick Bravardis, at the time had gotten a position. So when he left, I decided to go with him, but I was still a McMaster student. And surprisingly, what most graduate students don't know is that you are allowed to actually spend, I believe it's up to 18 months, if I recall correctly, of your grad school experience at another institution if you can make a case as to why you need to go. So whether if it's for specialty equipment or specialty people. So in my case, my advisor moved, so it gave me the opportunity to move as well. After I graduated, I did a postdoc at McGill till the end of 2014, after which then I went to go do a postdoc at the National Institute of Standards and Technology, NIST, in the US, Maryland, where I was also cross-appointed with the Material Science and Engineering Department at Northwestern University in Illinois. The postdoc turned to a research associate, and then at the beginning of 2018, I came back to the Canadian Nuclear Laboratories out in Chalk River. And I was there from then until essentially January 2022, and then I came back to McMaster.
Yeah, oh, that's awesome. So you've certainly spent your good chunk of your time in school and academia, for sure.
I have, yes.
So if I could ask, you spent quite a bit of time at McMaster specifically. Is there any reason why you chose to continue on with McMaster from your undergrad to graduate and so forth?
Well, I was asked to, so I said yes. So at the end of undergrad, and while the undergraduate program at McMaster is fantastic, I personally didn't think it gave me enough. So I still had questions that I didn't think the undergraduate program quite covered. And so when I was given the opportunity to do a master's, I kind of jumped at the chance. And it wasn't necessarily that I was looking for a master's, actually. It's just in my last year, I took a computational course with my master's advisor, Nick Bravardis, who also became my PhD advisor. And I found out that I really liked computational material science. And then one thing led to another. He had a project that was coming up, and voila. In terms of PhD, again, partly because I don't think my master's was going well. And so I wasn't really looking towards a PhD. And then again, fortuitously, my master's took like a 90-degree turn. It started going very, very well. And then again, one thing led to another, more funding and more projects, and a PhD was offered. And at that point, why leave? I liked my master. I like the culture, and I like my advisor. So why leave? And arguably, I think while there are good material science programs out there, I think arguably McMaster's, if not the best, but I'm biased, it's one of the best in the world. And so why leave a good thing? And so I decided to stick around.
Oh, that's awesome to hear. Yeah,
Yeah,
no, thank you for your responses. That's awesome.
yeah, that sounds great. Just to like move further deeper into like your background, what exactly is your area of research?
So my area of research is broadly in computational materials science or materials physics, whichever you want to call it. And really what that means, I guess, broadly is I apply programming and theory and condensed matter type models and things like that to materials problems. And so one of the big problems over the past, I guess, 15 years or so that I've applied it to is mostly solidification, but I've also done some work in precipitation reactions, looking at things like surface energy. Um, and over the past, I guess, 4 years, I've also applied it to some nuclear materials research. And in general, all that means is if we've all kind of taken a mass transfer course, you kind of have an equation that describes the diffusion process. And while it's very nice that the diffusion equation can be solved for simple problems like slabs, once you get into difficulties of, say, shapes that are different or complicated geometries, um, kind of doing it by hand isn't sufficient, so you need something else. And that's where computation, in my mind, gets involved. Another way I think computation also gets involved is when it's either in extreme conditions. So for example, nuclear materials research is one of the things that I find, or that I think that computation is very useful, because you can't do a lot of research um, in those sorts of environments. And so if you could find some other way to do that kind of research, so applying some sort of computational model that it may not bring you exactly where you want to go, but at least it could bridge some of that gap and perhaps maybe inform some of the experiments so that you're not doing so many experiments, but you're in a specific set. I also find that computation is good for prediction as well. So while we could definitely use it to validate experiments, and therefore then we could use models to do different things, I think in terms of its predictive capabilities, it's also quite fantastic. So in terms of, say, for example, predicting a new microstructure that could do new things. For example, batteries comes to mind a lot. I've come across lots of different computational work that have been predicting like microstructure for batteries. And so I hope I've answered that question.
Yeah, yeah, definitely. It sounds like your work is very programming centered. And just a follow-up question to that, is there like a very like particular framework? Like, do you use like specific language to build your models? Is there like this, or do you use like what kind of toolbox do you use to
Uh,
for your
so I've
programming?
so I've actually used plenty. So I started off with Fortran
Oh
and
wow.
C. So I actually learned C while I was in high school, and I think the undergraduate program at McMaster, I don't know if they still do that. First year was C based. I don't know if that's still C based.
For us it's Python, but I think if you're
Yeah,
in comp sci, it's C.
yeah. And so when I first got into computational materials program, it was Fortran, then C, then C++, like C and all its variants. Um, and I started off writing my own codes. And so I guess an example is I was mentioning the diffusion equation. So if you want to solve the diffusion equation, you need to essentially discretize it, so make it discrete so that a computer can solve for it. And so we were writing all those codes ourselves, whether in Fortran or C. Lately, I've gravitated towards two languages, Julia and Python. Python because there's several packages that kind of abstract some of the nitty-gritty work away from me. So I no longer have to write my own kind of finite difference codes or finite element codes or finite volume codes and so on and so forth. There are packages that I could load directly in, and not that packages didn't exist for C or Fortran, but they're somewhat more archaic and not as readily user friendly, in my opinion. And so I've gravitated towards Julia and Python. But I'm actually more excited about Julia, only because Julia is still somewhat a relatively new language. I think about 10 years old. And so I'm really looking forward to see what could be done with Julia.
Yeah, that sounds great. You have quite a large array of tools at your disposal. Just moving on a little bit, is there anything in particular that drew you to work in academia? Because I've noticed you've done a lot of work and at least like hands-on work, right? So is there a specific reason?
So I'm gonna answer that question by way of a story. I hope that's all
Okay.
right.
Yeah, that's
Oh,
fine.
for sure. Yeah.
So when I was doing my PhD, I actually didn't want to get into academia. My idea was, or at least my dream was, I like doing research, and so I like doing the research myself. And so I always saw the academic life as somewhat you delegating that job to your students. And I just really like the research. I like the figuring out the problem and so on and so forth. And so about a year or so left in my PhD, I came back to McMaster for some workshop or something like that. And I don't know if you guys know Dr. Gary Purdy. And
I don't think so.
No.
so he's emeritus in the department, and I came to know him when I became a graduate student as well. And so he worked with Dr. Zurab a lot. I'm pretty sure he was Hatem's supervisor, if I'm not mistaken. But anyways, after one of the talks that I had given at this workshop, him, Hatem, because Hatem was also my co-supervisor during my master's, Jeff Hoyt, who was a professor at McMaster, he was also chair, and he sat on my PhD committee, and my advisor, Nick Provadas. We were all talking about what I had just discussed and things like that. And they were all very curious as to what I was going to be doing. And I told them what I just told you. I wanted to find a nice, cushy research job, probably at a lab somewhere, and just continue doing what I was doing, you know, finding cool problems and trying to solve them, or at least take them as far as I could. And while they were all very, I guess, receptive to that idea, they all didn't agree that that's what I should do. And so Gary at the time said to me, because I explained to them that I didn't want to do academia because I think it kind of drew you away from research and kind of put all the administrative stuff that kind of prevented you from doing research. And Gary at the time said, while he understood that, he asked me the question of where do I think I would be if himself, Hatem, Nick, and Jeff, if they all chose also not to go into academia, but to do research elsewhere. And that really gave me pause in terms of how I looked at research and academia. Because up until then, I guess you might say I might have been maybe a little selfish or closed-minded in terms of really what research was. And part of research, through that conversation, what made me realize is that part of research is also teaching. And so from then on, I thought, okay, maybe academia wouldn't be that terrible of an idea. And so I slowly started gravitating towards it. And I had always enjoyed mentoring other graduate students, because at the time I was like a senior PhD member, and I didn't mind mentoring kind of like master students and undergraduates, but I never really saw myself as a professor. And so that's when it started, but then it slowly kind of diminished when I had applied for some positions and nothing came of it. And so I decided, well, maybe it's not time for it, and so I just went into industry. But the idea of academia still was something in the back of my mind. But I thought when the time was right, maybe I'll come back. And lucky for me, someone reached out when a position became available, and here I am. So sorry about the long-windedness of that answer.
Yeah, no problem.
That's perfectly fine. I think it's great that we have you here now. Just moving on, I'm just gonna pass on to Jeremy to ask you some further questions more related to industry or work-related questions.
Okay.
Yeah, so generally speaking, either at your current position or maybe some of your other ones, what does a kind of standard work day look like for you?
So that's actually changed a lot. And so I'll take you back to when I was a PhD student, because I think that's really when it started. And so a standard workday was quite fluid in the sense that you would attempt to obviously wake up at the same time and do the same thing. But the way I tend to at least describe it to some students is that there's no standard time or fixed time when research can occur, but you also need to make sure that it's not all consuming, right? That you take breaks, that there's also other aspects of life. And so when I was a PhD student, particularly when I was at McGill, my standard day actually revolved around me waking up and going to a coffee shop for about 8 to 10 hours a day with my laptop and just doing whatever it is I was doing. So whether it was debugging computer code, reading manuscripts, doing calculations. When I was at McMaster during my PhD, the standard day obviously then was interjected by whether it was TA work or anything like that I needed to do. When I became a postdoc at McGill, that really didn't change. It was same thing. I was at the coffee shop. And one of the reasons I enjoyed the coffee shop, particularly in Montreal, was because one, it's Montreal. How many times are you going to get to go to Montreal and literally hop around from coffee shop to coffee shop and kind of sample all the delicacies kind of thing? But it just also made at least my work somewhat distraction free. And it's almost kind of an oxymoron or contradictory that you're working at a coffee shop, but you think is distraction free. But for me, somehow working in those spaces made my work distraction free. When I went over to the US, my workday was more of, I guess, your standard, almost like 9 to 5. One of the reasons why, because when I went to the US, I had the choice to either sit at the university at Northwestern or sit at the lab in Maryland. And I chose the one in Maryland because the lab had a handful of researchers that I actually wanted to see face-to-face and interact with. And so, and they were also quite senior. And so they did kind of like the 9 to 5 type thing. They showed up to the office. And so that's also when I got into showing up to the office. And those there again, my days usually consisted of similar things where reading manuscripts, doing calculations, having conversations with my colleagues and finding out ways that we could collaborate, things like that, attending seminars and things like that. And at that point, I wasn't as riddled with kind of quote unquote administration type work in terms of like meetings and getting these things all sorted out. And so at that time, it was quite nice. And when I was at the university, similar things. I went to the university but there was always times the evening where, again, you never know when inspiration will strike you as a researcher. So my family would always say I carry like tiny little books and things like that around because you never know when ideas might strike you that you may need to jot down before you forget, so on and so forth. But breaks are always good. But the kind of university research life kind of gives you a little bit of free reign to kind of do that sort of thing, almost kind of like work when you want to work to kind of thing. But when I came back to Canada to the lab was very stringent because of both its past and both the type of work that it does. So the lab, because it's a nuclear research lab, rules particularly about safety and what you can do and when you can do it and things like that were, I want to say restrictive, but it was restrictive for what I was used to. And so there I was not as free to choose kind of like my own work and when I could work and how I could work, just because of the rules associated with that. And so there for me, it was a learning experience as well, because that was the first time I was in an environment like that where it was explicitly like, you show up at this time, you work for this many hours, you clock out, and then you go home. And so there, what I had to do, because I still wanted to do some research that may not have been tailor-made for the lab, but the lab will still get results, was I reached out to my old supervisor at McGill and started collaborating with some of his students as well. And so the work at the lab was interesting because projects would come into the lab or funding would come into the lab and they would already be slated for some work. And if I wasn't lucky enough, particularly in the first year I was there, to have already put in a proposal for something, that would mean that I was being given work that hopefully would have been aligned to my strengths, but sometimes was not a lot at all, which a handful of times it was good because then it gave me the opportunity to learn new skills, but other times it wasn't good because then I'd be staring at a project that I may not have known anything about, but I had to figure it out.
Right.
And so that's kind of been my experience up until coming to McMaster.
Interesting. So now, would you say that a lot of your work has been solitary, or is there like a strong like teamwork aspect to it?
Well, so in computation, at least the way you can't survive by yourself. And the reason why I say that is, how do I put this? So particularly when it comes to things that are engineering adjacent, like material science, while yes, I could sit down and write my own codes and things like that, that's fine. But a lot of the work that I'm doing is already either built up on or is taking work from other people that I'm working on. It's rare that in computation, unless you were the first person to do it, it's rare that you're doing it by yourself. And so partly one of the things actually in a lot of the computation groups that I've been privileged to be a part of, one of the things that has always been attempted to establish and usually has been established quite well is kind of like a camaraderie along with everyone in the group, where particularly because you're not the first person to come across a particular problem, there's no reason why you should suffer with it for so long before finding the solution. And so one of the things that was established at McMaster, and I think nobody uses the room anymore, is there's this room in the basement that has this gigantic table. And that actually used to be the room where the computational scientists sat. Often not, just everyone around the table, where everyone's, yes, we're working on our own thing, but then you come across a problem and you just put your head up and you ask a question, and someone gives you an opinion and someone gives you an opinion and someone's like, oh yeah, I came across that when I was working on something else. And the nice thing about computation is, even though I'm using, say, a different code or I'm writing it to look at a different process, kind of like coding is kind of coding, errors are kind of errors in that respect. And then when it comes to the science part of it, again, it's, oh, I may be looking at precipitation, but you may be looking at solidification, but kind of the underlying physics is kind of the same. Energy barriers need to be crossed and so on and so forth. So when you kind of talk to people and kind of interact with people, we kind of overcome those kind of little pitfalls or energy barriers that you may have, or obstacles rather quickly. And so while I guess in my description may have seemed solitary, because I feel like I'm working by myself, it hasn't been solitary. it's been somewhat collaborative. And like if you take a look at, I guess, my CV, I haven't like written a paper just by myself, and I can't take sole credit for everything that I've been responsible for.
Right, right. Very cool. So I just have one more question before I pass it off to Kevin here is, what do you say to people when they ask you, what do you do for a living? Because computational materials is kind of like a niche subject, kind of within a niche subject. So how do you kind of explain to people what you do and what you're about?
So I've actually have had several answers to this question, but nothing has really landed well. And that's the interesting thing. And so for the people that are in engineering or in the sciences that somewhat are well aware, you say computation, really, what do you do? And then the answer there is, okay, well, I solve PDEs on the computer to predict something. And then usually they get it. For the kind of layman or for the public, it's been a little difficult. And so one of the explanations that I've tried giving is I use computers to try to predict materials, microstructure and behavior. But then the inevitable question is, what is microstructure? And then you have to get into trying to describe what microstructure is. But I think the simplest one that I could give is, and to borrow from a few things that I've said, is as a computational scientist, I try to use computer resources, whether if it's programming, whether if it's image analysis, whether if it's just visual presentation. So I try to use all that in order to actually see how materials behave the way they behave. And I think that is usually succinct enough to both stop people from asking more questions, but also give them an overall good idea of what I do as a computational material scientist.
Okay, yeah, that's awesome. Because yeah, even trying to explain people what is material science to begin with, I find it can be a challenge as well. So
yeah,
yeah,
and
it's
so
interesting.
with material science, it's usually where I tend to go with that one is I tend to always ask people, as a material scientist, things always come down to materials. Whenever you want to do anything that's engineering related, usually it always comes down to what are you going to make it out of. And so once you ask them that question, you're usually talking to a material scientist. And usually when you lay it like that for people, I think they kind of better understand what exactly material science is, or at least where it fits into the kind of hierarchy of engineering disciplines.
Yeah, yeah, for sure. No, that's awesome. So I'm actually going to pass it off to Kevin to ask you some questions for maybe new people who are interested in computational materials. So yeah, Kevin, it's all you.
Yeah, sounds good. So what kind of advice would you give to, say, like a new student in first year who's considering materials engineering or computational material science? Like, what should you tell them, like, to develop on their own? Say any hard skills, any soft skills that they would need, or would help them succeed in this field?
So in terms of hard skills, I think, and I'm thinking back to what I wished I would have had more of when I got into computation, and that would have been more hard skills in computing. And that's not to say you need to be like an ECS or anything, but I'm talking about computing in terms of numerical analysis. And so you could always learn a programming language. And so for me, the idea of learning programming languages is not the important thing. Also because a lot of, like particularly Python and Julia, are as like syntactically, they're almost like English. So, and with the internet, it's easy to look up. But like numerically computing courses where you actually learn properly how you kind of discretize equations, how to do error analysis. That for me was the bigger hurdle. And so, and those sort of courses aren't necessarily offered in a materials engineering course. You usually tend to find those in either math or computer science courses, or actually sometimes even mechanical engineering courses where they have more experience in kind of computing, or at least historically. The other hard skill I would suggest for students looking at this would be things that are more physics oriented. And again, a lot of computational material science is actually computational physics, or at least that's the borderline. And so a lot of the computational material science stuff is usually borrowed from physics or condensed matter literature. And so one of the things that I've thought long and hard about is if I were doing, if I know what I know now and I was doing this again, would I actually prefer to take a physics degree and then do material science, than essentially doing material science and somewhat adjacently doing physics. But again, those aren't necessarily courses that are found in material science courses anymore, like a statistical mechanics course or condensed matter course or things like that. But again, some of those courses, for example, may be offered in physics courses, or actually possibly even in kind of chemistry courses or things of that nature. And so those hard things, or those hard skills, while you will pick them up along the way, having that kind of as part of your arsenal already gives you a good foundation. In terms of soft skills, well, I guess having some, and I'm not sure if this is a hard skill or soft skill, but I think it's a soft skill, but just generally being aware of just computers, like, because unlike experimentalists, your main tool is the computer. And so just being able to kind of navigate around what you can and cannot do with your computer, or what you can and cannot install. So for example, for the longest time, I was using Windows, like a Windows laptop. And I'm always connecting to a Unix system on the back end. But I needed to install at some point maybe 3 or 4 different types of software in order to make that connection seamless, where one was the terminal, then one was the file transfer, and things of that nature. And all because for me, I was very biased against getting an Apple computer. I didn't like Apple's ecosystem. I didn't like, their culture and blah, blah, blah. But the one system I don't have to install any software on, they make that entire thing seamless. And so for me, while it's not a hard skill by any imagination, I think just becoming more familiar with computers and things like that would probably not necessarily pay dividends, but it'll make your life easier. I guess soft and hard skill is just having an appreciation for mathematics. And again, a lot of computation is math based. And again, not necessarily a hard skill, but it is a skill you are going to have to develop. And so that's a whole other thing. So if you stick with traditional material stuff, you'll be good because you would have picked up all that math anyways. But if you decide to branch out in more interesting work, so for example, electrochemistry, which I think we do maybe 3 or 4 chapters worth in Gaskell, but if that's the path you want to take as a computational material science, well, guess what? There's like a lot of math involved in that science that makes it interesting, but it's that math then that you're going to have to kind of work out. And inevitably, I think another soft skill is just being able to communicate. And so as a computational scientist, unlike experimentalists, our communication is a little different. And so experimentalists, it's usually easier, in my opinion anyways, and I think experimentalists will maybe disagree, but I think experimentalists have an easier time communicating not only their results, but their research and why it's important, because they're physically actually doing it and then as they describe it. But as a computational scientist, it's similar to the question Jeremy asked in terms of how do you describe what it is you do? And so while I think if you're coming in as an undergrad, you may not necessarily have you may not have that vocabulary already or the ideas for that. I think a soft skill that if that's something that you plan to get into, you might want to pay attention to in terms of if you're getting into computational sciences, how do you communicate what it is you do, and not only what it is you do, but why it's important, and not only why it's important, but why is it needed. And so a lot of times as computational scientists, we need to make a case for why what it is we do is needed, while usually experimentalists, it's just tell me why it's important, not necessarily why it's needed.
Very interesting.
That really hits home to me. And in addition to these hard and soft skills, is there, would you recommend, or say you're hiring a student for an entry position into something computational material science related, would you require them to say have some more education past undergrad education, so say a master's or a PhD? Is that something that you think it's very important in the current state of things in the world of computational materials engineering, or do you think an undergrad position can do a lot?
You mean like in an industry setting?
Yep, in an industry setting.
So in an industry setting, I think it doesn't necessarily matter what your education level is. It matters what the, I guess, level you're entering. So if it is an entry level, undergraduate is fine. But undergraduate is fine, assuming that you have at least some of the experience that they're looking for. So for example, I know of plenty of people that have done PhDs in computational material science, for example, but they find it difficult getting entry-level positions in data science.
Wow.
Interesting.
And the reason why it isn't because they don't have the necessary skills. Yeah, they know how to program. They know the basics of programming, because data science, I don't know how much you're aware or how much your audience is aware, but data science isn't really that programming intensive, right? But where the disconnect is the application. And so a lot of PhD in computational material science up until probably 5 to 10 years ago, you were not being trained to necessarily be data scientists. You were being trained to be computational researchers, where you write a computer code, you run it for some results, you do some analysis, and et cetera, et cetera, et cetera. Data science is a different beast, where it's all about what you're doing with the data you get. And usually it's about large amounts of data, and how are you kind of not only whether if it's cleaning up that data or analyzing that data or inferring certain results from that data. And a lot of computational material scientists aren't necessarily trained for that, or not that they're not necessarily trained for that, but that hasn't been their bread and butter. their bread and butter has been look at the physics or look at the science. And so that's why there's been a lot of these kind of data science type incubators popping up, and not just for computational material science, right? These data science incubators have seen everyone from either people that have been doing like accounting or medicine or whatever, just get in there, because again, there it's not about the skills, it's just about what your skills have been applied to and maybe what they have been applied to. And so as an entry-level position, it all depends on what is being required of you, and not so much do you have the necessary skills, because as a computational material scientist, I trust that you would have those skills. It's have you applied those skills to these things yet? And while in most careers, you're always going to be trained to do certain things, I think what's happening and this is just my opinion, in data sciences, they already kind of expect you to have some of those applications already, and then they train you to do other things with that.
Exactly.
Does that answer your question?
Yeah, that's kind of what I expected, because I've been looking myself like for some positions after my co-op, and I noticed like a lot of them, there's quite a wide variation. Some of them require just undergrad, some of them are master's, PhD level. So I just wanted to know your opinion on the level of education required. So
well, yeah, and I think so the idea of entry level, I think, is subjective, and until you get the company to kind of describe to you what they mean by entry level, you may not ever know if your definition and their definition actually match. My definition of entry level is just that, entry level. I will train you to do the things eventually that you should and need to be able to do. That is the old definition of entry level.
yeah.
But I think given the kind of proliferation of data science, if those are the kind of things you're looking at specifically, and I think maybe we're picking on data science, but data science, I think, is the closest thing to computational material science if you're looking for work outside of like academia and research, right?
Yeah.
I think given the proliferation of that, they expect entry level to also mean other things. And so, for example, so I know of a researcher who, again, had his PhD doing computational material science, right? And that's the thing, your PhD isn't in computational material science, or your master's in computation, right? Your master's in material science.
Yeah.
Right.
You're then trying to convince the person trying to hire you that you did computation.
Right.
And so that's a hurdle as well, because then they're now trying to make the distinction of, okay, you did material science degree, how much computation did you actually do? And is that computation actually useful for the kind of work that I want you to do? But the example or the story I was telling is the PhD where he was doing computational material science. But then what he was doing was he was also doing essentially side projects on his own, eventually thinking to himself that he wanted to branch out into data science, so that when he applied for a job, he could show that, yes, I did computation during my PhD, but I also did these handful of projects that kind of showcase my, I guess, enthusiasm for data science in general.
Mm.
Yeah, that sounds about right to me. I think Jeremy and I have worked on quite a lot of personal projects outside of class just to help build that resume, to help convince people. So yeah, that's
Definitely,
great.
yeah.
Anyway, I'm just gonna pass it on to Jeremy because we're running a bit low on time to ask a few more questions.
Sure. Yeah. Thanks, Kevin. So generally speaking, like, what's your favorite topic that you are the most excited about in like computation, material science, or just material science in general? What really gets you going?
So I'll pick two topics. So the
Sure.
first topic is actually something that I've been, since we're on the subject of like data science and machine learning and all that. So for me, all that is under the umbrella of data science. I know some people like to nitpick of, I'm just calling it all data science. And so I haven't gone into data science yet. I've been reading manuscript after manuscript on how people have been applying data science methods to material science and et cetera. And so while I was at NIST, a colleague had tons and tons and tons of data on additive manufacturing samples and what conditions they were manufactured at, and then their mechanical properties, so yield strength, toughness, failure. So, but there was no way for him to essentially collate and kind of make sense of all that data. And so how long have I been away from this? So 7 years. So for the past 6, 7 years, I've been saying, okay, yes, I will find a project, or I will kind of carve out some time and I work on this project, I work on this project. But life being life, something always more important or more pressing, or something that's actually paying your salary or whatever actually comes up. And so I've been putting that off and off and off. And so one of the projects that I'm excited about getting done, and I have a master's student hopefully to start September, but if not January. And her job will be to do this project. And I'm very excited to see, one, is all the things I'm reading about for data science. Is it actually plausible? Because it's one thing to read about it, but it's also another to actually apply yourself to actually see what this methodology is capable of doing. And so one of the things, or the thing that I'm looking to do, is essentially take all that data and kind of map out, okay, these conditions led to this microstructure led to these conditions in terms of mechanical properties. And then for where there are gaps, either see if the machine learned system could fill in those gaps with actual microstructure, or where there are gaps, since one of my expertise is in microstructure development, can we actually run simulations to develop that microstructure and feed that into the kind of data science apparatus and have it spit out what the properties are. So it'll be kind of like the chicken or egg. So where there are gaps, can we give it the property and have it develop the microstructure, or can we feed it the microstructure and have it predict the right property? And so I'm excited about that. The other thing that I'm really excited about, and coming from my last job, was in nuclear materials research. And as most people know, at least in Canada anyways, one of the ways that we are trying to kind of circumvent climate change is with more nuclear power. And so there's this new class or new technology of nuclear reactors called small modular reactors, which by the name, like, they're supposed to be much smaller, the size of like shipping containers type thing. The thing with that is it's a new technology. So they're still essentially being designed. And one of the things I'm excited about is trying to develop advanced modeling techniques to look at the materials that are going to be involved in those type of reactors and the new technology. And so those are the two things that I'm currently excited about.
Interesting. Oh, that's super, super cool. So I'm just kind of curious with the nuclear materials specifically, as somebody with like computational expertise, like where do you begin saying, okay, we want to investigate these materials more? How do you generate like a materials model? Like, where does it all generally start for you?
So for the nuclear stuff, it starts with what we already know from conventional nuclear reactors. And so conventional nuclear reactors, one of the things that's been studied most is not just the fuel, so the microstructure of fuel and what happens to the fuel as it's been irradiated, but also the kind of housing, the cladding around the fuel. And so there they tend to be kind of zirconium-based alloys. Also in some reactors, there's also like kind of like steam generation type thing. So you're also dealing with like stainless steel type materials. And so in the new technology, someone, and it's trying to think, can't come up with a name, but it was some people in the DOE and DOD, I think, type things. There's already been extensive research in over the past 15, 20 years looking at new materials already and candidates. Mm-hmm. And so essentially the thermodynamics somewhat is already done, or you have the candidates for new materials. And so we have some understanding of the physics that occurs during irradiation. And so for someone like me, the starting point is then figuring out or getting to, okay, what are the thermodynamics? And so all materials have kind of these free energy type relationships that you're looking for. The physics in terms of the kind of flux of energetic particles or neutrons that are incident on a material, that's already done. And so that is a starting point. And then you're just trying to cook up kind of like the minimizing energy principle, that you have this kinetic term and you have these free energies, and how do they kind of work out in the materials process. The thing there is then you're choosing, at least for me, what scale you're working at. And so if I tend to work on the scale of microstructure usually, but there are some researchers that work on the scale of atomistics, where then they're actually looking at the actual radiation process. So if like a single neutron hit your material and then it caused all this damage, how does that damage kind of correct itself? While me, I'm looking at it after kind of the damage has already kind of corrected itself, and you just now have like a higher energy system. How does that affect like the microstructure evolution? And then there's still kind of a higher scale where you don't really care about the microstructure. You're kind of caring about how temperature gradients are changing, or how the defects are changing mechanical properties or strain and things of that nature. And so it always starts off with what you're interested in as a researcher. And so for me, it's usually microstructure and how that evolves, or how that changes, or phase transformations. And then you go from there.
Very interesting. Yeah, definitely. It's always interesting to hear about, like, especially with like nuclear materials, with all of the kind of bad press it has in the past, to hear about all of the development and that sort of thing that goes into it. So
yeah, and so for at least for Canada, both the Ontario government and the federal government, and at least our university, Master University, they've all, I forget what it is, they've all signed on to essentially this pact or agreement to advance nuclear technology. And so it seems like it's important, and Canada's always played a role in kind of nuclear technology anyways. And so this is just kind of the next step.
For sure. Great. So I'll pass it back over to Kevin to talk to you a bit more about some like bigger ideas and maybe the future of computational material science. So yeah, over to you, Kevin.
Yeah, just a couple more questions for me. So firstly, what do you think is the biggest challenge or problem currently facing computational material science?
Ooh, the biggest challenge or problem.
Yeah.
That's a tough question. To be honest, I haven't really thought about it. Maybe it's because I'm so siloed in that respect. So not currently, the biggest challenge always in computational material science is real-time computation, right? And so sometimes a lot of the promise of computational material science is we could give you the answers without you having to do experiments. But then the response, particularly from industry, is, well, I want the answer immediately. And then as a computer science, I'm telling you, I can't give you that answer immediately. Give me, you know, maybe a few weeks to a month, or maybe a few months, and I could do a simulation. And so the biggest challenge in general would be time. And this is why data science is becoming so popular, because I could go to an industry. So let's take an industry like steel making, where you have kind of the operator sitting up on their booth, and you know the steel is coming in hot and they're rolling and all this. They have, let's call it 70 years of data. If I apply a data science or machine learning type algorithm to learn all the data from every single steel mill in the world, presumably I should then have a competent enough model that could be used in real time everywhere, depending on what it is you're interested in, right? And so maybe you're interested in like how hot compared to the thickness and compared to like the rolling time. Who knows? It's been a while since I took steel making, so forgive me.
No worries.
But for a computation, give me a couple of weeks. I'll put in all the right kind of finite element calculations of the heat transfer model and all the finite element calculations for the strain that you need to compress. And then I'll give you an answer, but it'll be an answer to maybe a certain set of conditions, or maybe for one particular kind of rolling mill. I can't give it to you for the next one. I'm gonna have to redo the calculation. And so the biggest and I think the penultimate kind of dream of any sort of computational material science is real time, at least if you're trying to sell it to someone directly in industry. And I say sell it because at some point that is kind of like the give and take. But it's always the industry partners that are more interested in looking at fundamental science. So they might want to learn some underlying principle of why, say for example, when they make certain steels, it tends to fail or it tends to blister or something, that the machine learning model may not be able to tell them that they might need a more kind of fundamental analysis. And so their computation, the way it is now, is perfect, where you take your time, you put on the right physics, and you're like, okay, yes, maybe it's the chemistry and you didn't realize that, or maybe it's the set of temperature conditions. And so, yeah, real time, I think, is the big thing. But adjacent to real time is always doing bigger and bigger systems that approximate real time. And so I'm specifically talking from the point of view of either the computational scientists that tend to do either atomistic or mesoscale, i.e. microstructure simulations, right? The drawback that often we always have is we don't have enough computers to do system sizes that are representative of the actual experiment. I'll give you an example. So some experimentals will say, come to me and say, all right, I have this sample that, you know, probably maybe centimeters by centimeters, or maybe a few millimeters by millimeters. Excuse me. And that's what they're doing their analysis on. And then they're asking me, okay, I need to look at the precipitation that occurs in the sample, because according to them, the sample they have is representative of the actual macro scale system. So as a computational scientist, I would need to do a simulation that's representative. But depending on my resources in terms of computers or my ability to program my simulation, I may be restricted to only like hundreds of nanometers by hundreds of nanometers. So I may be only be able to do like 10 grains in terms of microstructure.
Yeah.
That's not really representative when they have thousands or tens of thousands of grains in their sample. And so one of the other things with computation in my mind is also kind of that scale. And so the US has been very good, and the Chinese as well have been building up their kind of computing resources. And so in the US, they have this new exascale computing systems. And the idea of that is, like, most computers do however many kind of floating point operations per second. And so the more floating point operations you could do, that means the bigger you can make these systems so that they don't take forever. Because arguably you could do a system that's, say, a centimeter by centimeter, but on a regular, say, teraflop system, and that may take you years to do instead of months. While the exascale, because it does, I guess, an order of 3 or however it is more times floating point operations, you can now do bigger systems at this for the same time, for example, that you might be doing the smaller system now. Canada's not quite there yet, or at least our investment in those type of things isn't quite there yet. But that's because I think we don't have like a DOE or DOD with, you know, trillions of dollars to spend on research.
Yeah, absolutely. So just to like quickly summarize, you're saying that it's pretty much sometimes you have limited data or limited computational power, or even sometimes limited manpower to actually do the work and make like a new simulation each time you
Well,
encounter these set of constraints.
Well, the manpower I think is second, but it's definitely limited computation power. So, and you could think of that as either not enough computers or not big enough computers. And by big, I don't necessarily mean size.
Yeah.
And then in the first case, in terms of the real-time stuff, it's so for example, if we had quantum computing, we wouldn't be having this discussion, because theoretically quantum computing is supposed to be near perfect. You could do how many computations and then you'll be done. And so in terms of, like, I guess my first point, in terms of real time, that is always the ultimate thing of computation, depending on who you ask. Can you actually give me these answers in real time? And I'm not entirely sure the kind of computation I currently do will ever actually actualize into real-time computation, unless I've done all those computations and I say, kind of give you a representative plot or something of that. Does that make sense?
Yeah, that sounds just about right. Hopefully in the future we have better, I know that for sure there will be better infrastructure for us to use to help solve these issues. Yeah, but yeah, that's the final question for me. I just want to thank you for your time. You have been very engaging, and I believe our audience will learn a lot from watching this interview. And just to pass it on to Jeremy to have our final closing remarks.
Yeah, so thank you so much. And then again, like Kevin said, I both of us hope that this will help students who are interested in the field learn a little bit more. And there's nothing like having somebody with experience like you with the field, and you know, the whole experience from going from undergraduate, graduate, PhD, industry, that whole thing. It's super great to have had your time. So we sincerely thank you.
It was my pleasure. Thank you for inviting me.